isoscalar. All right, so welcome everybody to our seminar, our topical seminar on the hadronic, nuclear, and atomic physics group at the University of Barcelona. Today we have the pleasure to host Antonio Márquez Romero from the University of North Carolina, Chapel Hill. Antonio did his undergraduate in Sevilla and then a master's at Granada, and later joined for a PhD at the University of York under the supervision of Jacek Dobaczewski. That's where we met, I think, somewhere around 2016, probably, or 17. And since then, he finished successfully his thesis in 2020 and has been a postdoc now at North Carolina for around 2 years, right? And Antonio will be talking today about how to make the calculation of nuclear matrix elements for neutrinoless double beta decay easier. Thank you, Antonio.
Okay, well, hello, everybody. And first of all, I would like to thank Arnau and the people responsible behind the organization of these seminars for this opportunity to present the work that we've been doing at North Carolina, and which will involve, as he said, the calculation of nuclear matrix elements easier. And I understand that nuclear matrix elements can be an ambiguous concept, but it is related to the neutrinoless double beta decay. So first of all, let me give you a little bit of history, a little bit of context, and it all starts with neutrinos. So I think we all know what neutrinos are. These were the particles that were introduced in order to explain the continuous spectrum of beta decay. And while originally they were conceived as particles without mass, later experiments have shown that these neutrinos oscillate. So there are like 3 families of neutrinos: the electronic, muonic, and tauonic neutrinos. And then it's been measured that a neutrino can oscillate between these 3 families. But the thing is that this mechanism can only happen if neutrinos have mass. And while we don't know the mass of these neutrinos, we only know the relative differences because of experiments with solar and atmospheric neutrinos. But what is more interesting about these neutrino particles is that they are chargeless, so they don't have any charge. So in principle, they are the only known neutral fermions. They're also fermions. So in principle, these particles can be their own antiparticles. They can be what they are called Majorana particles, while all fermions in the standard model are Dirac particles, so they are different from their antiparticles because they are also charged. If you have a proton and then you want to make an antiproton, then the proton will be the charge of this proton will be inverse. But since neutrinos have no charge, they do not possess this problem. However, up to this day, we don't know. We don't know if neutrinos are their own antiparticle. We don't know if they are Majorana particles. This is an open question. And in order to know if they are Majorana particles or not, the best course of action lies on the neutrinoless double beta decay reaction. So what is the neutrinoless double beta decay reaction? Well, it is a decay in which, in a nucleus, in which 2 neutrons have decay into 2 protons, emitting 2 electrons, and no neutrinos. So that's why it's called neutrinoless. So this neutrinoless double beta decay can be explained in terms of single beta decay. In single beta decay, we have a neutron which decays into a proton, and an electron, and an antineutrino in this case. However, this antineutrino can go to this side, can go to the left, and then be absorbed. Well, it can go to the left, and then it will be a normal, unusual neutrino, which will be absorbed with the neutron, emitting a proton and an electron. And this is what is happening here. So we have the first neutron, which decays into a proton, an electron, and an antineutrino. And then this antineutrino is absorbed with this second neutron, emitting the second proton and the second electron. But then obviously we can see from this reaction here that this can only happen if the antineutrino is equal to the neutrino. That is, if neutrinos are their own antiparticle, they are Majorana particles. So if this process is observed, then this will answer this open question. This is a unique fingerprint of the Majorana particle nature of the neutrinos. And therefore, there are lots of serious experimental efforts to measure this decay, which up so far, it hasn't been observed yet. But there are like serious efforts in order to do this worldwide. But then in order to measure this, they need some input from the theorists. And this is where we rise and shine. This is where they need us. So what experimentalists need, at least, is the rate of this process, which is related to the inverse of the half-life of the decay, which in a simplified picture can be seen as a product of three things. First, we have these G quantities, which is just like a phase space factor. It's a like very complicated integral with all the kinematics of the reaction, but everything is under control here. There's not really any approximation that we cannot take control of. So everything is okay with the G factors here. It also depends on the effective neutrino mass, because again, neutrinos oscillate. So we're not gonna find a neutrino in a mass eigenstate. In general, it can be a superposition of the three families of neutrinos that can be found. And then the degrees of mixing are given by the matrix entries of this U matrix, which is called the Pontecorvo matrix, but is completely similar to the Kavivo-Kobayashi-Mascaba matrix that is applied in quarks, and that may be more familiar to you. So this is a completely similar oscillation mechanism that happens in neutrinos too. And then finally, we have the very famous, but they're also infamous, nuclear matrix elements, which have this expression here. Well, it can be disentangled into Fermi, Gamow-Teller, and tensor matrix elements, which are like the largest contributions that go into the total nuclear matrix element. And it can be written using this expression here, depending on the operators that are applied to the initial state, to the ground state of the initial nucleus before decaying. These tau operators are the isospin raising operators. So these operators transform neutrons into protons, and this is what was happening in this decay. The two neutrons were decaying into two protons. And the sigma matrices here are the usual poly spin matrices, so carrying spin, carrying angular momentum. These quantities here, this H, are the neutrino potentials, which have like very complicated expressions, but in general depend on the relative distance between the two nucleons. And then, so what is the problem with the nuclear matrix elements? So there are lots of ways, there are lots of nuclear models that we can apply in order to obtain these matrix elements. But the thing is that all of these models have their own approximations, and they are difficult to keep track of and difficult to relate to each other. So in the end, when you try to compute the matrix elements using all of these models, there is an uncertainty of a factor of 2 and up to 3. I think it's been reduced now, but still, this is a large factor inducing a large uncertainty in the nuclear matrix elements, and therefore in the rate of this process. So we need to refine these matrix elements in a way, and it can be done in two manners. First, we can refine these neutrino potentials here, or well, the nuclear matrix elements will depend on the ground state wave functions of the initial and the final state. So you can work on methods or in better approximations to obtain the ground state wave function of the initial and the final nuclei. And this is where we've been focused all of our efforts here at North Carolina. So in order to do that, in order to compute the ground state wave function of the nuclei, of the initial and then of the parent and daughter, we're going to use what is called the immediate similarity renormalization group in order to process the chiral interactions that we're going to use, these ab initio interactions. And we are very interested in using these chiral interactions because they have a control uncertainty. This can be a little bit controversial, but I think the community agrees this is like the best way to proceed, to use chiral interactions. So the concept behind this method is very simple. So by means of a unitary transformation U, which depends on just a single parameter S called the flow, we are going to decouple the low and high energy momentum of the interaction, making the Hamiltonian diagonal or block diagonal, effectively diagonal. This Hamiltonian is obtained by solving this differential equation, which depends on this object eta, which is called the generator. And there are several choices for this generator, but usually it can be taken as a commutator between the diagonal and off-diagonal parts of the Hamiltonian. Now, it is called in medium because it's applied in nuclei, but you can apply this similarity renormalization group to a matrix. Imagine this is a matrix, and then you can obtain the eigenvalues of that matrix. So it's another way of diagonalizing in that case for a usual matrix, Hamiltonian matrix. So we're going to use this to process the chiral interactions we're going to use. And then in order to compute the ground state wave function, we're going to use the generator coordinate method. In the generator coordinate method in the GCM, the ground state wave function is computed as the linear superposition of mean field states that have some degrees of freedom that are constrained. Now, usually in mean field states using a Hartree-Fock or Hartree-Fock, usually Hartree-Fock-Bogoliubov method, there are lots of symmetries that are broken and need to be restored in order to properly account for the correlations to the ground state wave function. And that is done by using these projection operators for the number of protons, neutrons, and angular momentum. So the GCM, what it does is to obtain these factors here, which completely define the wave function. And in order to do that, we build the norm overlap matrix. So the overlap between all of these mean field states with these quantities Q that are constrained. And then after we build this norm overlap matrix, we diagonalize it and we obtain some sort of orthogonal basis called the natural basis or the natural states. Using these natural states, we can then diagonalize the Hamiltonian in this basis, and then we obtain the energy of this ground state, of this wave function, which again, this wave function is the ground state of the nucleus, of the total nucleus. But then these natural states can not only be used to obtain the energy, but if you also use it with the double beta decay operator, you obtain the neutral matrix elements. But now the problem is that these operators here, these projection operators, involve three-dimensional integrals for the angular momentum, but there are also integrals for the neutron and proton numbers. So these integrals are hard to compute. So it all depends on how many states do you have here. And the number of states that you have here will depend on the degrees of freedom that you're going to constrain. So now the obvious question is which collective degrees of freedom are important in general, but specifically in our case, in neutrinos double beta decay. Well, it's been found, well, the formations are always important, but especially triaxiality in those nuclei that show it. So, well, beta is the axial deformation, and then we have triaxiality here given by this number gamma. So in this case, for example, for germanium, which is a potential serious candidate to observe, to measure this neutrinos double beta decay, we observe that the minimum of germanium is at gamma equal 30. So this nucleus shows triaxiality, and if we want good correlation, we would an accurate measure of the nuclear matrix elements, we need to include sadly triaxiality onto the ground state wave function. But also it has been found that isoscalar neutron-proton pairing can also affect a lot to the nuclear matrix elements, and therefore it must be included if we want like a good computation, a good calculation of these nuclear matrix elements. But then we may not stop there. Why not including isovector pairing or octupole deformation? I mean, what's the limit here, right? But then the problem is that if we're going to include all of these correlations, this will we need to take more and more mean field states, and therefore this will be a computational burden when we compute the ground state wave function using a GCM calculation. And we can make a quick estimate of how many matrix elements we need to compute. Imagine this case of germanium, for example, and we are going to take 6 points in beta, 7 points in gamma, and then let's say we want to include neutron-proton pairing with 5 points. So then we have 6 times 7 times 5. So that would be around 200 states that are included in the superposition in order to compute the ground state wave function. So 200 states here. But then in order to compute this ground state wave function, we need to build the norm overlap matrix, the overlap between all of these 200 states. And this will involve 200 square projected matrix elements with their own integrals. And this is, well, this is a lot. And this, we need to think about a smarter way to do this. Not only because we want calculations to be faster, but also because we want to include more and more correlations, and maybe we want to compute other nuclei, maybe heavier nuclei, and then calculations are even slower than that. Well, luckily for us,
Antonio, can I ask just something? So how does this burden or the computational cost compare with the medium SRG one, which is also very expensive computation?
It's well, I wasn't really involved in the calculation of the IM-SRG interaction, but they're doing that, and it's also, it takes months. While it's the whole burden it's taking now in the IM-SRG processing of the carrier interaction. That's true, but it also depends on the number of states that you want to include, right? So it's also beneficial for the IM-SRG calculation to reduce this number of mean field states.
Of course. I just wanted to get a feeling. I didn't know which of the two steps was the dominant one in time.
Yes, okay. So when you are doing an IM-SRG calculation, it's in the processing. In that case, that takes the whole burden, the whole computational burden. Yes.
Yeah. Thanks.
It's taking, just as a side note, it's taking months now to process this interaction. Yes. Okay. So in general, it takes a computational burden if we are using many mean field states. So, but luckily for us, we know that not all of these states will be relevant when building this ground state wave function. Let's take this example here of calcium. And we have the energy of calcium as a function of the natural states. So this is like the orthogonal basis that we have after solving the Hill-Wheeler equation. So after diagonalizing the norm overlap matrix. So, and we see, for example, let's say this case of the first 2+ state, that we increase the number of natural states and then the energy hardly changes. Now, this is also something that is done in order to say that the calculation was successful. We know already that the energy of calcium for the 2+ state has to be around -2. But then we can exploit this fact, and instead of before diagonalizing the full norm overlap matrix, we can say we can restrict ourselves to a subset of these states and then diagonalize a much smaller norm overlap matrix in view of these results, because we can see that not all of them are necessary because we reach a plateau, well, in this case, rather quickly. So then again, how are we going to select the most important states? Well, we have developed a method in order to do that, which is based on 3 criteria. Well, first, the energy of these states. So we're going to take states that are near the minimum, which we suppose they are more important. And this is like a very reasonable assumption, right? This is the way nature works. Everything that's close to the minimum energy, so everything goes to the minimum. So we expect that in the minimum, things are more important. So we're going to take, in the case of germanium, for example, states around here. And in selenium, because, well, germanium decays into selenium. That's why I plot these 2 nuclei. And in selenium, we would take states around here. So the second criterion would be based on the double beta decay operator, because again, we are interested only in the nuclear matrix elements. So we want to select states that give a major contribution to the nuclear matrix elements. And we have found, well, in previous references, but also in our analysis, that this can be done if we take states in the initial and final nuclei, which have the same deformations, so the same collective coordinates, so which they're called like partner states. So again, with this example of germanium and selenium, if we take states in germanium around here, so beta 0.08 and gamma around 30, we need to take similar states in selenium around the same range of deformation. So around beta 0.08 and 30, so around here, even when they are not close to the minimum. But we have found that by doing that, we make a larger contribution to the neutral matrix elements, so they converge faster. And I understand this is an ad hoc assumption, but this has been found in previous references, and also we have found that, and we're going to show that in the results. And then the last criterion would be based on the orthogonality of these states. We don't want to include a state that can be represented by a linear superposition of the ones that are already there, that are already selected. This can be seen, for example, in the usual XY plane. So imagine that we have a vector in the y-axis and a vector on the x-axis. These two already serve as a basis for the whole XY space. If you include another one that's say diagonal here, this one can be represented by linear superposition of this one and this one. So this is not adding new information to the system, so that it can be discarded without anything happening, really. So this is what we're going to do with this last criterion. So for any candidate state to be included in the set of selected states, we compute the projection of this state onto the subspace of selected states. And this will give a number between 0 and 1. If it's very close to 1, it will be discarded, because that means that it can be represented by the set of selected states already. So in order to be included, it has to be below certain overlap cutoff with the set of selected states. So with these three criteria, we developed what we call the energy transition orthogonality procedure, which we called ENTROP. And then we a method to select the important states, especially for the nuclear matrix elements. So, okay, so what's the algorithm of this method? What does this method do? So first of all, we need a set of mean field states, and we need all the energies and all the norms in order to compute the overlap, and also because we want the states with energy near the minimum. So, and what we do is, so we have a set of selected states in the initial nucleus and in the final nucleus. This is empty. Now we're going to take as the first state the one with the lowest energy, both in the initial nucleus and in the final nucleus. And then we stay in the final nucleus, for example, and then we take the partner state of the state with the lowest energy in the initial one. So the same with the same deformations will be included in the final nucleus, but again, only if it is orthogonal enough. So if this projection L onto the space of selected states is lower than a certain cutoff that we choose. If not, it will be discarded, and then we don't consider it anymore. And then again, we go to the initial nucleus and we consider the partner state of the state with the lowest energy in the other nucleus. And then we go in that fashion now in energy order. We take the second to lowest energy state, and again, only to be included if the overlap with the two states that are already selected is smaller than the cutoff. If not, discarded. And then we take the partner again, and then we take the energy order again and partner again. And we go in that fashion until we run out of candidate states. Now, because we are discarding states because of this orthogonality criterion, we're going to end up with a set of fewer states than the original ones considered here. So the question that arises now is the one that is obvious. So can we afford to do that? Can we? So if we do that, do results hardly change, or do they change a lot? So for that, we need to test this method using a full calculation with all of these states, and then let's see the resulting results using the state selected with ENTROP, using this algorithm here. So now I'm going to go to explain the test that we did. But first of all, I understand that this method can be confusing. So if there are any doubts, or if you want me to explain that better, or if there are no questions about this, I can proceed. I understand this is confusing. I still find it confusing, but basically, so we have the initial and final nuclei. we go in energy order, then we take the partners, so the states with the same deformations in the initial and the final nuclei, and then we go energy order, partners, energy order, and we go like that until we run out of states. Okay, so the thing is, can we do that? Can we afford to do that? So we need to test this method, and the test that we chose is, well, the nucleus is going to be germanium, which decays into selenium. The interaction that we're going to use is a shell model one. So it's called the GCN 2815, and it's just a balanced space with an inner core interaction. And it comprises these orbitals here. And well, yes, of course, the collective degrees of freedom that we're going to constrain are the quadrupole deformations, so axial and triaxial deformations, but also isoscalar pairing, so this neutron-proton pairing. And in total, we have, well, as I said before, almost 200 states, so 184. So the good thing about this shell model interaction is that not only we can compute the full calculation using 184 states, we can also compute the exact results for the energy and for the nuclear matrix elements. And we can compare with both. So, well, for the energies in germanium and selenium, well, the ground state energies here, we have found that that using the natural basis with all of the states, so doing a full GCM calculation, so normally the diagonalization of the norm overlap kernel with all of these states, and then we do again the norm overlap matrix diagonalization with only the states selected by entropy, and then we can see here, comparing these two results, that for the convergence of the energy, that with our method it does as well as with the natural basis one, as diagonalizing the full norm overlap matrix. So the states selected with our method are around 50 in germanium and 30 in selenium, out of 184, both in germanium and selenium, but still it works, at least the convergence, it works as well as when using the natural basis one. So if we want more accuracy on the energies, we can just reduce this norm overlap cutoff in order to include more states. But then again, we're not really interested in the energies, we're more interested in the nuclear matrix elements. But still, I think it does a good job, not only on the ground state energies, but also on the spectra for germanium and selenium. This is the comparison done with the states selected with entropy and the exact results. So diagonalizing the exact shell model Hamiltonian. And we can see that, well, there is an overall shift here of around 1.5 MeV and 2 MeV here. But still, the distribution of states is quite, I would say it's quite good, even for excited states. But then again, we're not really interested in the computation of energies. We're more interested in the nuclear matrix elements. And then we can see that in that plot, that convergence with the state selected with entropy is actually very, very good. So after 20 states selected, we can see that the total matrix element has already reached the full value represented by the dashed line. This dashed line is the full value computed using all the 184 states in germanium and in selenium. So in total, it would be around 360 states. So, but we only need around 80 states in order to get well, the full result with a huge plateau here, with huge convergence here, which will tell us that this is the actual good result, the actual the good value. It's already reached the actual value. So we have also included the case of selecting states by using only the energy, so without including partner states. So just in energy order. So we take in germanium and selenium states going only in energy order. They will only be taken if the overlap between these states is less than this certain cutoff. But then we can see that if we don't include these partner states, that was a criterion that we have chosen in order to make the convergence of the nuclear matrix elements faster. We see that it's not as good. and maybe cannot be seen here, but the accuracy is about 30% better when using our full method, when using entropy, including partner states.
Antonio, one question.
Yeah.
Do you have a way to know what's the properties of the states that contribute more to the matrix element? Because
yeah,
I guess at the beginning you just don't know that you can basically stop at 20 states with entropy.
well,
But is there a way to know this or to get a feeling about the states that contribute more?
the only way to know this is by judging by this convergence here.
Okay, but there's no additional property that you have a feeling of before doing this kind of study, the convergence.
No, I understand this is a little bit complicated because this convergence judging was only made for the energies, but because in the case of the energies, it's a variational thing. If you include more states, the energy can only go down. So then if you see a plateau, then that means that you have reached the proper energy. This assumption maybe cannot be made about the nuclear matrix elements, but judging by this good convergence for around 50 states here, I think we have the confidence to say that we have reached the actual value. This, of course, we cannot prove that. This is an ad hoc assumption, but it seems reasonable.
Okay.
Yeah, but Javier and Antonio, if you look to the plot, do you hear me? Yeah.
Yes.
Yes.
It is in the upper plot. It is very spectacular. When you go to this state, when you add one state, and everything happens. So you have a plateau, one state, and another plateau. It will be very interesting to analyze this state, no?
Exactly, yes.
Yes, but and we've done that, but the thing is, it doesn't really depend on only one state. It depends on
looks like.
In this case, but if let's say that I remove that state, then this jump can also be seen because it doesn't depend only on one state, it depends on several or on a certain combination of states.
Because they are not linearly independent.
In this case. Okay, well.
Well, yes, no, they won't be linearly independent. No, we have a set of mean field states at the beginning, and then these are the ones that we choose. We do a GCM calculation with these states, but we do not select the orthogonal ones. No, we select the mean field ones. Yes.
Okay.
Yeah, thanks.
So we have run this test because it is quite spectacular that, for example, for this plot here, that there is a very, very big jump here. So it's fair to consider, so this is the state that changes everything. But we have done a test saying, okay, what happens if we remove this one? We don't see this jump. And that's not true. We also see this jump. It's just maybe that we see it like further down. So it doesn't really depend on only one state. It depends on a certain combination of those. So we really need to consider all of them. And then there's also another problem that you may consider, that is you can observe a plateau here and then there's a certain jump. So you need to really consider like lots of these states to really be confident about that you have reached the full result. Okay, so this is the plot for the total matrix elements, and then we have the one for the Fermi, Gamow-Teller, and tensor parts of the matrix elements. And then we can see that the convergence is mainly driven by the Gamow-Teller part of the nuclear matrix elements. It's also the one that contributes most to the nuclear matrix elements. And while these are the full results with the 184 states, for the Gamow-Teller and tensor parts, I think they're also very close to the exact shell model results. The Fermi one is not as close. I think it's around 50% larger, I think. But this can partly be explained because using this method, we break explicitly isospin symmetry, while in the exact shell model interaction, it doesn't. So this can be partly explained by that. But still, overall, they're very good results. So I think in view of these results, we can say that this method, like, it's working. So instead of having to take almost 200 states for the full calculation in order to obtain some results, we can only take, let's say, around 80, combining both in germanium and selenium, and we will obtain something very similar and with a huge confidence because of the large plateau, large convergence in here. So, so maybe we're confident to say that this method works. And then, oh, well, sorry. So this is another plot with all the information about the states that are selected with our method, with Entrop. So these are the deformation plots for several values of the isoscalar strength, the proton-neutron strength. This phi is the expectation value of the isoscalar pair creation operator. So the red dots represents the states that are taken by Entrop. And we can see that there are lots of states around phi equal 1, meaning that isoscalar pairing is important when computing the nuclear matrix elements. And I hadn't said that there is a relative size with all of these points, meaning that that it has a larger contribution to the ground state wave function the larger the size, the larger the circle is. So it's like the probability for the ground state wave function to be found on this particular state. This is related to the collective wave function probability. So so I think the takeaway message from this plot is that there are lots of states taken here with huge size, meaning that isoscalar pairing plays a significant role in the nuclear matrix elements. Not only deformations are important. Okay, so in view of these results, I think we can say with confidence that this method, well, is working, at least for the shell model case. So let's try it now with a chiral interaction for which full results are not available because of this processing with the IMSRG. So the chiral interaction that we have used is the one by Entem and Mashley, and we have done exactly the same. So it's the same nucleus, germanium decaying into selenium, and the same collective degrees of freedom, so quadrupole deformations and isoscalar pairing, and around the same number of states, around 180, I think. And we can see again that with the states selected with Entrop, 16 in selenium and around 18 in germanium, we have already reached like a very large plateau convergence there. So making us to believe that the full results for the energies of germanium and selenium, the ground state energies, are around these values here. But then again, we are interested in nuclear matrix elements, and we can see that maybe convergence is not as good with only 15 states in selenium and around 18 in germanium, but still there is a hint of convergence around this line here, around 3.19, which is what was observed with other phenomenological interactions, other phenomenological calculations. So maybe we're not 100% confident, but the full results have to be around 3.19. Again, we can disentangle the total nuclear matrix elements for the Fermi, Gamow-Teller, and tensor parts. And then we can see that the convergence is mainly driven by the Gamow-Teller part. And the results for Gamow-Teller, the Fermi and tensor ones are very similar to what is being observed with another calculation that is being published based on the balance space only, while we have the whole configuration space into consideration. The only problem is that the tensor one was really different, but our tensor result was in accordance with what is being observed with other phenomenological calculations. So I think we are very confident that this method, while we don't have a benchmark here because we don't have full results or exact results, as in the shell model case, we are confident that it's done a good job because of the large convergence, large plateaus seen, and they're very close to results that have already been published. So in view of these results that we believe that they are very successful, we are thinking about further applications of this method, because so far we have only applied it to we have only applied it to germanium, but what happens if we apply it to other nuclei, for example, calcium, that is like a very serious potential candidate for neutrinos over beta decay. And in fact, the deformations here are very different in the initial nucleus, calcium, and in the final nucleus, titanium. So can we take partner states here? So it's still a thing to consider, and we haven't tried that yet. But also heavier nuclei. In principle, we can apply this method to heavier nuclei, and it will be very interesting to see. But also, we have applied this method to for only our interest, which is in the nuclear matrix elements. But in principle, we can modify this method a little bit to compute any other observable that you want, such as electromagnetic transitions, but anything that you want, really. We haven't done that yet, but it's in principle a very interesting idea to do. We have tried a shell model interaction and a chiral interaction, but we haven't said anything about density functional theory. And there are potential applications here, especially with the GCM, because this is where GCM method really shines in density functional theory interactions. I have preliminary results already, but I have been working on this week, and I can say now that it also works for this case. We also see the same kind of plots with the same convergence as observed in the shell model and chiral interaction cases. Well, the whole idea about this method is because we could include more and more collective degrees of freedom. So we have included only quadrupole deformations and isoscalar pairing so far, but we would like to include isobector and octupole and whatever comes to your mind, really, because we can select only the most important states, but being the most consistent as possible. And I think we're going to explore this this region using density functional theory interactions. And then, well, this is something that we had in mind here, that there is a possibility that instead of constraining these observables using mean field states, you can let the dynamics be driven by the Hamiltonian and then take random states along the path formed by this Hamiltonian using this imaginary time method. So it's basically the exponential of this Hamiltonian applied to a random HFB state, unconstrained HFB state. So then you wouldn't be constraining anything. The values of these observables can be anything that you want, but then you would be selecting states along a gradient descent followed by this Hamiltonian. But in order to do this, I need to have a time-dependent HFB solver, and I don't have that so far. But it's not on the discarded pile of projects; it's on the to-do list of things. But still, it's something that is left to do. But we believe it's a very interesting idea because then we don't need to constrain explicitly the values of the observables. Okay, and with that, I think it's about time, right? So I will jump into my conclusions. So I think the takeaway message is that we have built a greedy algorithm in order to pick out the most relevant states in order to build the ground state wave function of the initial and final nuclei with the means of fast convergence for the nuclear matrix elements in neutrinos over beta decay. And this method depends on the energy of these states, on the double beta decay operator, so this transition operator, and the orthogonality between all of these states. So we don't want them to be very linearly dependent. And we have seen that we have obtained like very promising results using a shell model interaction for our benchmark, but also with a chiral interaction for which a full calculation wasn't available for us. And still we observe like a very good convergence towards reasonable values of the nuclear matrix elements, which led us to believe that this method is working properly. And now we're working with it in density functional theory applications. And then, well, so these results were good and they were accepted for publication in PRC. So it was accepted this month. So I guess it will be published next month on December. So if you could please read it and cite it, I would be very thankful. So with that, I would like to thank my collaborators, everybody that had to say something in this project, I would like to thank you for your attention. Thank you.
Thank you, Antonio. I'm clapping virtually here. It was a very interesting seminar on a new topic. Does anybody have any more questions for Antonio?
Hi, now I will just, you were comparing, you were using this interaction in a model space. Let's say the chiral interaction was in the model space, no?
Yes.
In the same model space, valence space, I mean.
Yes, yeah.
Yeah. But at the same time, in the paper, you were quoting, if I remember well, with this interaction, this valence space, whatever many other initials go, they had rather funny matrix elements, mainly for 82, but also for 66. And you look like getting very sensible ones.
So you mean in this paper for the balance
Yeah,
space?
yeah. What do they get really for this, for the number? Because you get sensible things, no?
I get, yes. Well, for the Fermian gamma of Taylor, I think they're almost identical
To the ones in the paper.
to the ones in this paper. Yes.
Okay, okay. Because I had in my mind that they got. Javier, do you remember that?
I thought they were a little smaller than these numbers, but I don't remember by heart.
Yeah, but
They're not exactly the same, but sorry.
Sorry, the big surprise or discrepancy or craziness was in 82.
Yes, in 82 was really much smaller than 76.
Okay, it was that. In 76 was not so bad, no?
Yeah, it was a little lower than the shell model, but not as much as the selenium. 82.
Okay, thanks, Javier.
But also, Antonio, so you say that just related to this question by Alfredo, that the matrix elements look very similar to that paper, but have you compared also the spectra?
Well, no, I haven't computed the spectra with the chiral interaction.
Because that would be very interesting, because the spectra that the valence space in medium SRG got were actually not very good.
I think we have discussed this here, but no, we never considered to compute the spectra. But maybe that's something, I have all the data, we can do that, we can compare, but we haven't considered that, no.
I think that would be interesting to understand whether this is something missing on the medium valence space truncations, or whether you would agree and this is related to the interaction.
Well, yes, because in our case we're using a full IMSRG calculation, so it could be, yes, you're right, it could be interesting to see. Yes, thank you.
Also, if I can ask something else.
Mm-hmm.
So you mentioned in the Outlook about the extension to the DFT. Yes. And that you already have results. The main advantage there is that you can take care of more collective degrees of freedom at the same time, right?
Because yes, that's what we're hoping for. Yes.
Okay, because of course the GCM has been applied there, but your advantage would be that you can apply the GCM with more degrees of freedom at the same time.
Exactly. So our main objective now is to include more collective degrees of freedom. And I think it's already been done in density functional theory calculations. So we're gonna, the fastest way is to proceed in this direction. Yes.
Okay. Yeah. Thank you. Yeah, it was very nice talk, by the way. Thanks.
All right. Thank you.
So I had a little quick question on the computational aspects. No, so you've talked about the number of states, but presumably there's other, I mean, you need to compute all the overlaps, you need the energies, I presume. So is it really much faster than, say, than the full calculation in addition, by just reducing the number of states? Do you have any estimate?
Okay. Well, I can tell you about the test that we did with the shell model. So with the shell model, I actually computed the full calculation using 184 states. Now, this all depends on how fast the integration computation is for the projection. But if instead of 184 states in germanium and in selenium, you only take around 15 germanium and around 14 selenium, then, well, if you run all of the jobs in parallel, then you won't see any more time advantage in that. But usually that's not the case in computer clusters, so they're in a queue. So while using the state selected with entrop, I think I run results for a couple of days using the whole 184 states in both germanium and selenium, because not only for the energies, I also need to compute kernels for the nuclear matrix elements for this same calculation there. I think it was for 3 weeks or almost a month to have results there with 184 states in the shell model interaction, which is a balance space one. So it's significant, the savings, even here in a very simple shell model interaction. Yes.
Right.
But again, it all depends on how you do the projections with these integrals. Maybe there are some good approximations for these ones. We have also considered those, but in the end, we thought that it was more convenient to just reduce the number of states needed, just exploiting this convergence criteria. Is that clear? I don't know if that's...
Yeah, I think so. Yeah. Are there any other questions for Antonio? Well, if not, then thank you very much, Antonio, again, for a very nice and interesting talk. I'll stop the recording now.